7-2. Use the converse of the Pythagorean theorem. By the end of today's lesson, we will be able to successfully use the converse of the Pythagorean theorem to determine if a triangle is a right triangle. The converse of the Pythagorean theorem states that if the square of the length of the longest side of a triangle, so referring to the hypotenuse again, is equal to the sum of the squares of the lengths of the other two sides. So the other two sides would be A and B. So this entire first part of the sentence just means c squared equals a squared plus b squared. Then the triangle is a right triangle. So for example 1, we want to see if the given triangle is a right triangle. So I'm going to first simplify by the greatest common factor of 3. I'm going to take 3 squared plus 2 squared. And I want to check if it's equal to the square root of 13. And it is. So this triangle here it is a right triangle. And for part B, we can first actually there's no GCF, so we're gonna have to just use a long way. I'm gonna take 24 squared plus 16 squared instead of equal to 29 squared. 24 squared gives me 576. 16 squared, 256. 29 squared, 841. And 576 and 256 makes 832. But this is not equal to 841. So no, this triangle is not a right triangle. And let's do 2 more practice. Well, I don't see any GCF, so we just have to deal with all these numbers given to us here. So I'm going to take 4 squared plus 5 squared and square 2 square root of 10. I'm going to square this. And this makes 41 on the left hand side, but it's not equal to 40. So no, not a right triangle. Okay, let's try one more, and I see that the GCF is 3, and I just make my life easier. I'm going to divide by 3 for all 3 values here. So all I have to do is take 6 squared plus 5 squared and the square root of 61. And I see that both sides are equal, so yes. Right triangle. Theorem 7.3. If the square of the length of the longest side of a triangle, so let's see here, be the longest side, and if we square it, and if it's less than the sum of the squares of the lengths of the other two sides, so a squared plus b squared, then the triangle ABC is an acute triangle. So again, if c squared is less than a squared plus b squared, then the triangle ABC here is acute. And for theorem 7.4, if the square of the length of the longest side of the triangle, which is C here, is greater than the sum of the squares of the lengths of the other two sides, A and B, A squared plus B squared, then the triangle ABC is an obtuse triangle. So it's the opposite of the previous theorem. So again, if C squared, the longest side of the triangle, is greater than the sum of the squares of the other two sides, A squared plus B squared, then the triangle ABC here is obtuse. Example 2, Part A. Can segments with lengths of 2.8 feet, 3.2 feet, and 4.2 feet form a triangle? If so, would the triangle be acute, right, or obtuse? Well, since the longest side length is 4.2 feet, I'm going to take 4.2 feet. I'm going to square that. And that's going to be 17.64. And I'm going to take 2.8. I'm going to square that. And that's going to be 7.84. And 3.2 squared, 10.24. I'm going to add these two shorter side lengths, the squares of these two shorter side lengths. And that's going to be 18.08. So then the longest side here, the square of the longest side is less than the sum of the squares of the two shorter side lengths. So we can conclude that this triangle is an acute triangle. Now for this next example here, I'm going to test 11.3 squared. And I'm going to do 6.1 squared, 9.4 squared. 11.3 squared is 127.69. 6.1 squared is 37.21. 9.4 squared is 88.36. And if we add these two numbers up, we get 125.57. And it appears that the square of the longest side is greater than the sum of the squares of the lengths of the other two sides, so we can conclude that this is an obtuse triangle. Example 3. You're helping install a light pole in a parking lot. When the pole is positioned properly, it is perpendicular to the pavement. How can you check that the pole is perpendicular using a tape measure? Well, let's first draw the picture. Now, let's just assume that this pole is 3 feet. Well, to show a line is perpendicular to a plane, you must show that the line is perpendicular to two lines in the plane. So again, back to this picture here, I'm going to let this pole be 3 feet, and I'm going to establish a Pythagorean triple here, 3, 4, 5. So now that I have this pole here, and to show that it's perpendicular to the pavement, meaning this entire ground or pavement, I've shown that this line, or the pole, this is the pole, is perpendicular to a plane, which is your pavement. So then, since this line is perpendicular to two lines, so this will be the other one line and this is another line, then this pole is positioned properly. Okay, let's summarize what we've learned here. The methods for classifying a triangle by angles using its side lengths. So if c squared equals a squared plus b squared, then measure angle C equals 90 degrees and triangle ABC is a right triangle. And in theorem 7.3, if the longest side, C here, C squared, is less than the sum of the squares of the other two shorter lengths, A squared plus B squared, the measure angle C here will be less than 90 degrees and triangle ABC will be an acute triangle. And in theorem 7.4, if C is the longest side here and we square it and it's greater than the sum of the squares of the two other shorter side lengths, then measure angle C is greater than 90 degrees and triangle ABC is an obtuse triangle. The proofs are given on the website.